Welcome to the fourth module, Blockchain Technology Basis. In this part of the lecture, we will try to cover the basic understanding of blockchain technology and smart contracts. We will dive deeper into cryptography and other key elements that form and enable blockchain. This module will be a tad bit more technical, as it is important to try to understand how this technology works. So what is blockchain? One of the definitions would go, the blockchain network is a hardware and software infrastructure that enables decentralized time-step transaction ledger and smart contracts to power the blockchain applications. So let's cover the key blockchain facts. Blockchain technology was invented in 1990 by a Stuart Haber who worked at Bell Labs. Blockchain technology can be defined as a hardware and software infrastructure that moves data and enables decentralized immutable timestamp transactions or balanced ledgers and smart contracts to power blockchain applications. It is the technology that enables you to verify the transaction claim of assets or other facts. For example, we can now verify the asset status on any of the public blockchain wallet addresses. It's called an inclusive accountability. Basically, we can check all the public ledger and verify any transaction at any time with an online tool that is called a blockchain explorer. This is a revolutionary concept because anything similar was attempted before. It needed to have a third party and an intermediary. So Bitcoin is the first example that was deployed that did not need a trusted third-party intermediary to resolve this. Blockchain is also secured by cryptography, which uses hash functions for tamper resistance and integrity and to connect new blocks to prior blocks. Blockchain uses public and private keys for consent. It is a data mechanism and a concept of how to store data composed of a chain of transactions and a chain of blocks. And finally, it is an internet trust technology layer. A blockchain is a distributed ledger with growing lists of records or blocks that are securely linked together via cryptographic hashes. Each block contains a cryptographic hash of the previous block, a timestamp, and the transaction data generally represented as a Merkle tree, where data nodes are represented by leaves. Since each block contains information about the previous block, they effectively form a chain, with each additional block linking to the ones before it. So blockchain transactions are irreversible once they are recorded. The data in any given block cannot be altered retroactively without altering the blocks before. So blockchains are typically managed by a peer-to-peer computer network for use in a public distributed ledger, where nodes collectively adhere to a consensus algorithm protocol to add and validate new transaction blocks. So blockchain is a ledger, a database of facts that stores the transaction history. Blockchain enables proof of transactions and public verifications of wallet status, which we also call inclusive accountability. It enables decentralized use cases such as immutable on-chain voting, immutable on-chain property ledgers, decentralized finance, on-chain immutable supply chains, decentralized identity, and decentralized communication. The key blockchain building blocks are cryptographic hash functions, block and transaction timestamps, block headers Merkle trees, asymmetric cryptography and digital signatures, wallet addresses, consensus mechanisms, nodes and networks. So cryptography is associated with the process of converting ordinary plain text into encrypted text and vice versa. It's a method of storing and transmitting data in a particular form, so the only one for whom it is intended can read and process it by decryption. So in other words, cryptography can be defined as communication of secret information in the presence of an adversary, rival, or an enemy. So the cryptography has been known since ancient times. People have used it many techniques to hide their messages from their opponents. So let's address one of the key building blocks of any blockchain. So the cryptographic hash function. We can say that hash is a fingerprint for data, a mathematical efficient computer process that takes, maps information and turns it into the letters and numbers of a certain length. Hashing is used to make storing and finding information quicker because hashes are usually shorter and easier to find. Hashes also make information unreadable, so the original data can become confidential. So the process compresses, encrypts the data and provides a unique digital fingerprint. The process maps input X of any size into an output of fixed size called hash. It is deterministic, always the same hash for the same X. Hash can be efficiently computed. So SHA-265 or secure hash algorithm function 265 is defined as one of the most secure ways to protect digital information. SHA-265 is a mathematical process that generates a 265-bit, 46 characters long random sequence of letters and numbers, EI hash, out of any input. It is pre-image resistance, goes only one way, infeasible to determine X from hash X. It is collision resistant, not impossible but infeasible to find any X and Y where hash X equals hash Y. We could say that it has an avalanche effect, so changing X slightly and hash X changes significantly. So to simplify, hash is used in the middle of the proof of work or proof of stake consensus. Hash is used to compress data within the Merkle tree, squeezing it significantly. Hash is used to mint wallet addresses. So moving on to block structure. A block is a place in a blockchain where information is stored and encrypted. Blocks are identified by long numbers that include encrypted transaction information from previous blocks and new transaction informations. Blocks and the information without them must be verified by a network before new blocks can be created. Blocks generally include these elements, but they might vary between different types. Okay, so we have block size sets the size limit on the block so that only a specific amount of information can be written in it. The block header contains information about the block. The transaction counter represents the number of how many transactions stored in the block. And the final element of the blocks are transaction itself, which are represented as a transaction list within the block. So Merkle roots are binary data trees that compress and organize all the data and use the SHA-265. Every transaction is hashed and merged with the neighbor hash transaction into a new hash and so on. So if you have 1000 transactions, that's 2 to the 10th and 10 levels. So this task is usually performed by the mining pool operators. So moving on to blockchain consensus, block production, distribution, and acceptance. So when a user A initiates a transaction, information about the sender and receiver is packaged and timestamped on a block and sent to a queue called the mempool, short for memory pool, where it will wait for the to be validated and added to the blockchain. So miners or validators, depends on the consensus, that have successfully discovered all the blocks will take batches of the transactions and verify that all of the information, including digital signatures, messages, and public keys, are legitimate. Once the information is verified, the block is broadcasted to all the nodes in the network, who must check and agree that the block is valid before adding the block to the official chain. The average time it takes to confirm, let's say, a Bitcoin transaction is about 10 minutes. When the process is complete, users B will have received, let's say, 1 BTC sent to them by the user A. All nodes on the network will have agreed to the transaction using the chosen consensus model, and a Bitcoin miner will have earned a reward for verifying a successful transaction. So new blocks of information about the transactions are now linked to each other as a part of an infinite and public chain. So let's clarify the process within the Bitcoin proof of work. It is a process for achieving consensus by who is adding the next immutable block on a digital record known as a blockchain. Miners compete to solve a hard puzzle by computation, that's why it's called proof of work, while the network validates it easily. Mining difficulty increases. Bitcoin in January 2009 was 1. In January 2020 it was 1 trillion. That's because there are a lot of computers competing to win a reward. Let's also clarify that the process within the proof of stake networks. Solving the computation challenge with synthetic resources, staked assets, equals internal security that comes from the people that are vested inside the system and can be quantified in, let's say, US dollars. Chosen randomly, miners validate block transactions based on the number of coins that they hold, limited to percentage of transaction that is reflective to their ownership stake. So this brings us to the consensus part of the blockchain module. So blockchain operates as a decentralized network, enabling immutability, privacy, security, and transparency. There is no central authority for transaction validation and verification. Yet every transaction within the blockchain is considered secure and verified. This is possible only because of the presence of the consensus protocol, which is a core part of any blockchain network. The consensus algorithm is the mechanism by which all network nodes reach a unanimous decision regarding the current state of the distributed ledger. Essentially, the consensus protocol makes sure that every new block that is added to the blockchain is the one and only version of the truth that is agreed upon by all the nodes in the blockchain. So consensus mechanisms are solving Byzantine generals problem. They're solving how to coordinate actors if there are potential malicious actors involved, and they are deciding who is making the next block. So to go over to the consensus process again, we must first select someone to create a block. Then we must make the block, distribute it, and the network has to accept a new block. While there are many consensus mechanisms available, let's focus on the two main ones. So the proof of work, or short POW, is a consensus mechanism used in blockchain networks to confirm and validate transactions and add new blocks to the blockchain. It involves complex cryptographic puzzles that miners must solve to prove their dedication to the network and secure the system. Unlike the proof of work, where participants, miners, solve the complex mathematical puzzles to compete for the right to validate transactions and create new blocks, the proof of stakes operates on a different principle. In a proof of stake system, validators or stakers are chosen to create new blocks and confirm transaction based on the amount of the cryptocurrency that they hold and are willing to stake as collateral. In this type of consensus algorithm, instead of investing in an expensive hardware to solve complex puzzles, validators invest in the coins of the system by locking up some of the coins as stakes. So based on the actual blocks added to the blockchain, all the validators get a reward, proportional to their bets, and their stake increases accordingly. So there are a few advantages of proof of stake, like proof of stake is energy efficient. It consumes significantly less energy than proof of work. Proof of stake reduces centralization, as proof of stake networks can be more accessible to a wider range of participants. Validators in proof of stake have a financial incentive in maintaining the network security and validity. However, proof of stake also has its challenges, such as potential centralization around wealthy validators and nothing at stake problem, where validators have little to lose by supporting multiple forks of the blockchain. So moving to blockchain networks, let's clarify some general information regarding blockchain networks. So the first block in any blockchain is called the Genesis block. Consensus always supports the longest chain. Orphaned or stale blocks are discarded. Hard fork is a term used when an orphan or a stale block continues to be mined by a social consensus, remains to be present supporting a new chain. For example, this was the Bitcoin Cash scenario. Public blockchains allow anyone to read or write to the public ledger. They are decentralized, open, and permissionless. While private blockchains can restrict access to their network partners and are usually permissioned. They feature near real-time transaction processing, large data sets management, higher governance control, and fixed transaction price. This is usually the case. So let's discover the network players and their tasks. We have full nodes that store full blockchain and are able to validate all transactions. Pruning nodes, on the other hand, are type of nodes which performs almost all the functions of a full node. In fact, the only exception is that the prune node do not have a complete copy of the blockchain. Then we have the lightweight nodes that execute payments, verification, and store only blockchain headers. Miners or validators perform proof of work or proof of stake and create new blocks. Mining pool operators run the pool servers, which distributes mining tasks and tracks submitted shares. The operator also controls the pool's reward distribution and shares difficulty adjustments. Then we have wallets that store, view, send, and receive transactions and create key pairs. Mempool is a pool of unconfirmed yet validated transactions where pool operator gathers all the transactions and sends them to the miners so they can then add it to the next block.